this is a continuation of the last video where we were talking about Charles's law. And so we're going to do an example here, a second example. It says to make a 300 milliliters of oxygen. So milliliters is again a unit of volume. Degrees C is a unit of temperature, so 20.0 degrees C. So when you're doing these problems, I find students tend to skip the step. You notice the fact I put what variable it goes, what variable do we assign milliliters, which is a unit of volume. Degrees C is a unit of temperature, because if you're not sure what formula to use, seeing this in a formula will kind of be a clue of, hey, I need to do this problem, or I need to use this formula. To take changes its volume to 250 milliliters, so this even tells me it's volume, 250 mLs. What must the temperature be? Okay, in degrees C. All right, so with two volumes and two temperatures, okay, that means it's Charles's law. Again, these are in the same sentence, so they go together. So this is I, and this is F. So I have VI over TI is VF over TF. But the temperature must be in Kelvin, so I have to add 273 to get 293. Okay. So my initial volume is 300 mLs. My initial temperature is 293 degrees, K. My final volume is 250 mLs, and it wants to know what TF is. Okay. If you want to, you may cross multiply here. That would be one way of doing it. So I would get 300 times TF, is 250 times 293. So this side stays the same. And when I multiply these two together, which I didn't do it that way, so 250 times 293 gives me 73250. And then I divide both sides by by 300. Let's look at this. What do I expect the answer to be? Because this is good. If you got the wrong things paired, this will give you a clue. My volume decreased, and so if my volume decreased, I expect my temperature to decrease. So when I take 73250 divided by 300, I should get 244 K. Now this one did specify that it wants it in Celsius, so I'm going to take the 244 minus 273 to end up with a negative 29 degrees C. So in the last problem, if it doesn't specify, I could have left it in Kelvin, but this one happened to specify it. All right, the last one we're going to do problems with is called the combined gas law, and basically it's Boyle's law. So if I take Boyle's law is this, and Charles's law, which is this, and combines them together. Okay. Again, this is the formula that is given to you. This is how we typically use it. What's different about this one is that I have two pressures, two volumes, and two temperatures in this. Okay. So pantheonic acid is a B vitamin. Finding the Dumas method, which is what they show with the J tubes. Okay. I have a sample weighing, so I have 71.6 milligrams. Milligrams is a unit of mass. I have 3.84 milliliters. Milliliters is a unit of volume. I have 23 degrees Celsius, and that's a unit of temperature. And I have 785 millimeters of mercury, and that is a pressure. It says what is the volume, so that's what I'm looking for. At STP, STP will be defined shortly, but just for you to know that that means my temperature is 0 degrees Celsius and my pressure is 760 millimeters of mercury. Okay. So you see here I have 2 volumes, 2 temperatures, and 2 pressures. These 3 were in one sentence, so that's going to be my I. These 3 were in a separate sentence, so that's going to be F. And it doesn't matter mathematically if you label this F and that I. What does matter is that you have them grouped correctly. Okay? So I have PI VI over TI. Oops, I is PF VF over TF. My temperature, of course, has to be in Kelvin, so I have to add 273. That gives me 296 K. Add 273 to this one and get 273 K. So my initial pressure, you see that with these two, I do not actually need my mass. It was given to you, but you don't need it. Okay, so my initial pressure was 785 millimeters of mercury. My initial volume was 3.84 mLs. My initial temperature is 296 K. My final pressure was 760 millimeters of mercury. It wants to know what my final volume is. And my final temperature is 273 K. When I multiply and divide this or simplify this, I get 10.24. And this is going to be in millimeters of mercury times milliliters divided by K. If I take 760 divided by 273, I get 2.784. And again, that's in millimeters of mercury per K times my VF at the end of my slide there. I'm going to divide both sides by the 2.784. So I have 10.24 divided by 2.784 is equal to VF. So VF ends up being 3.68. Now, I wrote this down to realize that if they're on opposite sides, this cancels, that cancels, that cancels, that cancels. Ooh, that's a really bad number. 68. So what I'm left with is milliliters. So my volume is going to be the same thing that I'm given that unit of. Okay? All right. One more example of this. It wants to know what's the temperature. If I have 1,000 milliliters, so that's a volume of 1,000 milliliters of methane. I have 0.973 atmospheres, so that's pressure. And I have a temperature of 25 degrees C. It's changed to a pressure of 814 millimeters of mercury and a volume of 900 mLs. Okay. This one's a little bit tricky because it asks what the temperature would be when it's changed to these two. So therefore, it's this and that are linked together. So I'll make that my final. And that means that these three are going to be my initial. Okay. So again, I have 2 volumes, 2 pressures, and 2 temperatures. So it's PI VI over TI is PF VF over TF. I want to notice, however, that all the other problems until now, everything's been in the same unit. The pressure, the temperature, the volumes have all been in the same unit. This one, however, you notice I have atmospheres here and millimeters of mercury here. Either this needs to go to millimeters of mercury or this needs to go to atmospheres. I'm going to change this one because we're going to come up to problems in which we have to be in units of mercury. In units of atmosphere. So we divide by 760 and we get 1.071 atmospheres. Of course, my temperature has to be added to 273 to give me 298 K. All right, so I have a initial pressure of 0.973. I have an initial volume of 1,000. I have an initial temperature of 298. I have an final pressure of 1.071. I have a final volume of 900 milliliters, and it wants to know what the final temperature is. Okay, I'm going to simplify down this side. So when I multiply 0.973 times 100 divided by 298, I get 3.265. When I multiply 1.071 times 900, I get 963.9 divided by TF. When whatever I want is on the bottom, I need to multiply both sides by it, so I get 3.265. TF is 963.9. So I'm going to now divide both sides by the 3.265, so 963.9 divided by 3.265 gives me a final pressure, final temperature of 295 K. And this one does not specify what the temperature needs, what unit the temperature needs to be in, so I can leave it there. You can use the combined gas law for Boyle's law and Charles's law and either cancel them out because they're constant, or you can plug in the numbers, because a lot of the previous problems we were given the numbers for the ones that were canceled out. For example, here I was given a pressure of 760 and 760. I can put this into the combined gas law and just put in 760 for both of those. The other thing about combined gas law is for Boyle's law, Charles's law, I was asking you to predict what you expected the answer to be as far as larger or smaller. Combined gas law, since I'm changing two different things, there's no longer a direct or indirect proportions between, or inverse proportions, so I can't predict whether this answer is what I expect it to be or not. All right, and in the next video we will finish up this section.